In the last video, we have discussed about collision in one dimension, elastic collision mainly. And now we are going to solve this example based on the same concept. So what is happening here? Let me brief you the context. So in case of nuclear power reactor, fission reactor, what happens? I'm taking a single case here. A neutron hits uranium isotope 235. 235 is mass number. And then it gets merged into its nucleus, making it a new isotope 236. And this isotope is unstable and further breaks into barium and krypton. Okay, if I'm not wrong, this is mass number 92 and this is 141. Okay, so it breaks into these two things and then again we will get here three neutrons. And when these neutrons come out, they come out with very high speed. So to continue this fission reaction, these neutrons should be slowed down. And then to slow down these neutrons, we use materials like D2O, which we call heavy water, or like graphite. Graphite, as you know, it is a kind of iron, sorry, carbon. Okay. So we use such type of materials where these neutrons collide with the nuclei of these materials and then they get slowed down. Okay. Now coming back to our example. So here we are going to take an elastic collision of neutron with deuterium. Thereafter, we can take this one also because these two are very same process. The only thing is going to be changed here. In case of deuterium, the mass of deuterium nucleus is twice the mass of neutron, and in case of carbon, as you guess, it should be twice the mass of. If we are taking m mass of neutron, then deuterium nucleus has mass 2m and carbon nucleus has mass 12m. Now we will start with this thing. So here is the neutron. Let's take it as first body, and here we have deuterium nucleus. Let's take it second body. Now, what will happen? Let's say this neutron comes and hits, and keeping things simple, we will say that this collision is one-dimensional collision. Means they are moving after collision. They are moving along the same line. So such a collision where initial velocity of the bodies and final velocities, that is after collision, these two are along same line, not along the same direction necessarily, but along the same lines. So such a collision we call head-on collision. Okay, so here we are considering this that this collision is a type of head-on collision and elastic collision. So in case of elastic collision, let me write their masses. Let's say this is m1, this is m2. Initial velocity, let's say u1, and for this deuterium it is 0, and let's say this is neutron. So after collision, the final velocity of neutron is v1 and the final velocity of deuterium nucleus is v2. Now what we have to find, let's check again. We have to find, we have to show that a neutron can lose most of its kinetic energy. So let's check what is its initial kinetic energy and what is its final kinetic energy. So initial kinetic energy of, here we are talking about neutron. So initial kinetic energy of neutron is K initial for body first is 1 by 2 m1 u1 square, and final kinetic energy for this body is 1 by 2 m1 v1 square. Now we can compare when these terms are similar or containing similar terms. It will be easier to check their fractions. So what we need to do, we have to write here, instead of V1, we have to write this V1 in terms of U1. And for that reason, I'm going to take reference for our from our previous discussion. And where is it? Where is it? Okay, okay, here. Look, here we have discussed the same thing. So let's go to the next slide, and then here, no, you can't get here also. Here, no, okay, so you will get here. So final velocity of the first body, that is neutron in this particular example, is going to be m1, which is mass of the first body, that is neutron, minus m2, that is mass of the second body, which is deuterium nucleus here. And okay, this thing I'm going to write it. So v1 is m1 minus m2 divided by m1 plus m2 multiplied, whole term multiplied with u1. So I can write 1 by 2 m1, and then m1 minus m2 divided by m1 plus m2, and then u1 and the square of whole thing. So I can write square here. Okay, up to here, all good. Now we can take one more thing here. We can take fraction, or we can, yes, to get, maybe we can get percentage. Okay, so if we are trying to check what is final kinetic energy of neutron divided by initial kinetic energy of neutron. So for that reason, as you know, look, 1 by 2 m1 u1 square is nothing but initial kinetic energy of the neutron. So this ratio will be m1 minus m2 divided by m1 plus m2 whole square, and then m1, that is mass of neutron. Let's take this thing only m. Then m2 will be twice of m, because the nucleus of deuterium is twice, yeah, if you are comparing mass. So here we will have m plus 2m and square. So ultimately it is going to give you 1 by here 9. So final kinetic energy and initial kinetic energy, look, this is 1 is to 9. So if we want how much percentage is left, yeah, in terms of kinetic energy of the neutron. So what we can do one thing, we can take difference, and then we can make percentage from there. So difference I'm taking, as we know, initial kinetic energy is greater here. So we can do one thing. We can do initial kinetic energy of neutron minus final kinetic energy of neutron divided by initial kinetic energy of neutron. This is difference in kinetic energy, or change in kinetic energy, and then it will be positive. We have said already this thing multiplied with this. So this will give you percentage, and you know this is going to be 1, yes, k1, ki1 divided by ki1, and then here final kinetic energy here is 1 only of neutron divided by initial kinetic energy of neutron into 100. Okay, so you can solve it by yourself, because this thing, this ratio we have already here. Look, we have already here 1 minus, sorry, 1 by 9 here. So what you can do it, and you can write the conclusion. So ultimately you will get the percentage loss of kinetic energy of neutron. And if this is elastic collision, the same amount of kinetic energy is going to be appear in deuterium nucleus. Okay, you can do it for carbon by yourself. The only thing you need to change here, the mass of this second body. In case of deuterium nucleus, it is twice the mass of neutron. In case of carbon, it will be 12 times. Okay, you try that by yourself.